Hello everyone. My name is Yifan. My name is Yifan Dang. The title of my presentation is Entropy Extractor-based high-throughput post-processing for TRNGs. This is a joint work on behalf of my co-authors from Tsinghua University, COSIC, and Wuxi Micro Innovation. This is the outline, which is divided into 4 parts. First, I need to introduce the background of our research. In practical applications, many security protocols or authentication systems have been proposed to meet the growing demand for public channel secure communication. These protocols require secure cryptographic algorithms, and almost all existing algorithms rely on true random numbers that exhibit uniformity and unpredictability to generate encryption keys. So we can see that TRNG is the hardware's trusted root and the cornerstone of cryptographic security. This is the generic architecture of TRNG, which is composed of entropy source, digitizer, post-processing, and other test modules. The digital noise source generates the raw random numbers, but it with some statistical defects. Most current entropy source cannot generate idea random bits directly without post-processing. The post-processing module, also called conditioner by NIST, is a function that extracts randomness from raw random numbers. A functional and efficient post-processing module is crucial in a TRNG. There is 3 types of post-processing methods. First, there are simple algorithmic post-processing methods. They are easy to implement but have many limitations. Second, we have cryptographic methods with computational security, but they are more complex. The third type of post-processing is entropy extractor, which falls between the first 2 types, which is also our focus. They are more complex than algorithmic post-processing, but still more straightforward than cryptographic methods. The first problem of existing post-processing methods is the throughput. The random bits throughput is in communication centers is about 40 gigabits per second. Unfortunately, the throughput of IS standard complement TRNG cores fall short of these requirements, with the highest throughput being only hundreds of megabits per second, as shown in this table. A natural approach is using multiple parallel entropy sources to generate random numbers, but it will cause a new problem. If these sources are truly independent, post-processing is simple. A counter method can do it. But in reality, on a single chip, these sources are often correlated due to the shared power lines or temperature variations. Therefore, a post-processing module is necessary to extract uniformity from multiple parallel entropy sources with dependence and satisfy the required throughput. 2 previously proposed methods, Toeplitz extractor and the Trevisan extractor, can satisfy this requirement. Both of them belong to the entropy extractor. These are properties of 3 types of post-processing methods. The algorithmic methods are very simple and efficient with the information theoretical security, but can't handle complex collisions. The cryptographic methods can eliminate collisions, but no information theoretical security proof. There is no evidence that the output of cryptographic post-processing will exhibit higher entropy density. That means we cannot directly feed the non-perfect raw random number bits into cryptographic conditioners and hope they will do the magic work. The entropy extractors offer the best of both worlds. They can handle general collisions and provide unconditional security, which is not based on any computational assumption. Entropy extractors can extract near uniform randomness, often added by a random seed from another independent randomness source. So this is our goal. Now let's move on to the main contributions of our work. The first is the improvement of the Toeplitz extractor. The Toeplitz extractor is based on matrix multiplication. You take a raw random number vector and multiply it by a binary Toeplitz matrix, which is also the random seed. The leftover hash lemma guarantees the output will be close to the uniformity. We can use a safety factor Ypsir to present the output randomness. A Ypsir is the statistical distance between the output and the uniformity. A key is the mean entropy of raw random numbers, and key minus m is the entropy loss of our extractor. As for the development of Toeplitz extractor, you can see that previous research has pushed the throughput from 100 megabits per second to nearly 7 gigabits per second on GPUs. But the goal for many applications is dozens of gigabits per second. Moreover, due to the GPU's relatively high power consumption, we need an efficient solution on FPGA. To perform this large matrix multiplication efficiently in hardware, we use block division compiled with FFT acceleration. We divide the large Toeplitz matrix into small submatrices by rows and columns, and chunk the input vector in the same proportion. We just need to multiply a k by 1 subvector by a t by k submatrix each time. Then we can use FFT to accelerate this multiplication. Finally, we join and accumulate all the intermediate results to get the output. As for actual FFT acceleration, we take a 3 by 4 submatrix as an example. First, we need to transform this Toeplitz submatrix into a 6 by 6 cyclic matrix. Each row of the cyclic matrix presents different shifts of the same vector. Then we pad the input vector with zeros to expand it. Finally, we can use FFT to accelerate the multiplication of this cyclic matrix and this expanded vector, and we take the first 3 bits from the results as the final output. To reduce the signal length, we can use a modified Toeplitz matrix without weakening the security. M by n modified Toeplitz matrix comprises a M by M unit matrix and a M by n minus M Toeplitz matrix. In this way, we just perform the multiplication of this small Toeplitz matrix and the last n minus m bits from the input to get the intermediate result. Then we perform a module 2 addition with the first m bits from the input to get the final output. We design the simulation architecture of the Toeplitz extractor. The raw random number simulator simulates the output of the entropy source. We convert the output of present algorithm by data transformation to non-perfect random numbers. The random seed simulator stores the random seed and outputs a m by k submatrix at each cycle. We must point out that the raw random number and the random seed simulators are unitized only for simulation purpose. In a practical TRNG, these are directly from 2 independent entropy sources. The matrix multiplication mode receives a k-bit vector and a m by k submatrix and splits the submatrix into several smaller t by k submatrix. The vector accumulation module adds all intermediate vectors and the first m bits of the raw random number to get the final output. So this is the whole simulation architecture of the Toeplitz extractor. Our second contribution is the first ever hardware implementation of a Trevisan extractor. Trevisan extractor comprises single-bit extractors and a weak design. The weak design divides the total random seed into several sites with a little overlap and inserts each site into every single bit extractor. The total seed length is D. Each seed site is denoted as SI. The number of seed sites is M, and the length of seed site is T. We use the parameter R to denote the seed overlap, which is defined like this. Each single bit extractor takes a seed site to produce single output bit. The output bits of several single bit extractors are joined to compose the total output. If the overlap of seed site is not very large and the entropy in input is sufficient, drawing every output bit does not result in a large collision. The two dominant single-bit extractors available are XOR code and the polynomial hash. XOR code is very simple, which selects L bits from input according to the random seed and perform bitwise XOR to get the output. Polynomial hash has two-stage extraction. We need to divide the input vectors into S blocks in advance. The first extraction process performs polynomial multiplication and addition on the input sequence size in Gaudius field. Lambda is the seed of the first extraction, and the second extraction process performs the inner product of P1x and the second seed mu. The XOR code approach has a higher throughput, but it requires a very long seed and has higher entropy loss. While the polynomial hash is more efficient with the seed and the entropy, but it is more complex and slower. Therefore, we need a single bit extractor that strikes a balance between them. The single bit extractor proposed by this study works in two steps. The seed of the first extraction process is S1, and the second is S2. S1 is used to select one random bit from the input sequence of length n. The first extraction takes the L bits after this selected bit from the input sequence. This L bits is called XL. The second extraction is a single bit strong blender. A standard strong blender performs like this. X and Y are two segments of raw random numbers from independent entropy source. A is a series of shift matrix. A1 denotes a shift of 1 bit, and AM denotes m bits. For single-bit operations, we use only the first term. We perform the dot product between the XL shifted by 1 bit and the seed S2. To compare the performance of 3 single-bit extractors, we utilize the unified weak design. The weak design used in this work simply split the seeds and overlapping the initial part of the latter section with the final part of the formal section. We label the ratio of the overlap length to the seed length as theta. This is the simulation architecture of the Trevisan extractor. The raw random number simulator and the random seed simulator are similar to the Toeplitz extractor. The input data is fed to M parallel single-bit extractors. The random seed is also split into M segments, with each segment feeding one module. For simple configuration, our proposed method requires a seed length of just 237 bits, which is comparable to polynomial hash's 202 bits and far better than the 783 bits required by the XOR code. The last contribution of this work offers a general selection guide to assist TRNG designers in choosing the most suitable post-processing methods. Here, we provide an overview of the key features of common methods. 3 types of post-processing are all shown here. The red dots are algorithm post-processing, which have information theoretical security. We have cryptographic methods like SHA-2 and AES. Also, there are entropy extractors studied in this work that offers unconditional security. Algorithmic post-processing have minimum area and power consumption. They are suitable for systems where raw random numbers exhibit only bias or Markov collision. The Bloom algorithm is the only one capable of handling Markov collisions. In many applications that requires a constant output rate, so the methods like VN and Bloom algorithms are not ideal due to their variable output rates. When entropy source is of low quality, entropy loss becomes a critical issue, making proper line code the optimal. Making the proper line code is the best algorithmic post-processing method. On the other hand, when the entropy source is of high quality and hardware overhead is a primary concern, VN and XOR should be considered first. In more cases where complex collisions are present in raw random numbers, algorithmic post-processing methods are generally ineffective. If cryptographic primitives are already integrated into the application systems, lightweight cryptographic methods may be a suitable choice. However, the main drawback of these methods is their lack of formal information theoretical proofs for entropy extraction. For data-intensive applications where speed is over area and power consumption, or when raw random numbers are from multiple parallel correlated entropy sources, the entropy extractor implemented in this paper is a better solution. Next, I will present the results and the evaluation of our design. Here are the performance results for our Toeplitz extractor. We achieved a throughput of 42 gigabits per second. This is a huge improvement over previous work, and compared to other cryptographic post-processing methods, our design delivers an 84% increase in throughput to area ratio. Additionally, while our implementation consumes the most power due to the larger output length, this is not a major concern for high-performance applications such as data centers, where power consumption is often a secondary consideration. Trevisan extractor achieves a throughput of 1.82 gigabits per second within the scope of 3 Trevisan extractors. Our work achieves a 73% throughput to area ratio improvement compared to the XOR code and requires a seed that is 70% shorter. Also, our design consumes the least power among the 3 single-bit extractors. We can find the single-bit extractor proposed in this study combines both advantages. While the overall of our work may not match that of cryptographic methods, the Trevisan extractor has the key advantages of unconditional security. In contrast, cryptographic methods like formal proof of their entropy extraction. Finally, we give a conclusion. In this work, we present 2 entropy extractors with global application range and enhanced safety. Our Toeplitz extractor achieves a high throughput of 42 gigabits per second, making it ideal for servers and data centers where speed is the most important factor. Our Trevisan extractor achieves a medium throughput of 1.82 gigabits per second, providing an efficient solution for lightweight cryptographic applications, and it is the first hardware implementation of its kind. Finally, we provided a selection guide to help designers to choose the best processing method for their specific needs. And the artifact of this work is available. That's all. Thanks for your attention.